Excited because I'm happy to say that power finally makes sense to me somewhat. So usually we care about the power that's dissipated through resistor. And here's the interesting thing. Apparently, it doesn't matter if there's no reactive components, meaning no inductors and no capacitors, whatever. Whether you have one or not, if you're looking at the power over a resistor, it doesn't really matter. You're always going to use the same equations, and it's always going to be this. So the power usually it's an average power because you're looking at RMS, but here's the voltage supplied, I guess, ERMS, EMF squared, and then this is divided by R. This is the current squared times R, and then this is the voltage across the resistor, uh, which is the V equals IR, which is essentially the same thing here. So it's kind of like three ways to sort of write this. Now, this is across the resistor, regardless of whether there's attached components or not. But let's say we do attach a component. And if that's the case, then what happens is the new total current is actually going to decrease a bit because, we started with a V equals IR. Now we have this V equals I, I apostrophe here times Z. So it's going to change the current a little bit. But usually we don't really care too much about the total current. If we want to look back at the resistor and figure out what the power distributed across the resistor, we only care about the real component, which is the stuff going across the resistor. And to find that, you just find the real component of this stuff, which you have to use the power factor uh, to do that. And so that's why now it kind of makes more sense that when you're looking at the say power supplied or power dissipated, it doesn't matter across the resistor. This is kind of more for power supply. We use these formulas here. This is more for power dissipated, but it's exactly the same thing because it's supposed to be equal, right? So yeah, it makes more sense here because see, look, we have V times the current here, but we had to scale it by the power factor. This is across the resistor. And if you're looking at the other side, then you do I times the sign component, it's across the inductor or capacitor or whatever if you want to. These things apparently do no work because this is 90 degrees tangent, I believe, to something. Let's not worry too much about all that stuff. Don't really know what the heck that all means, but this is usually the stuff that does work because it's real. The stuff that doesn't work because it's imaginary. That's kind of what's going on here. So the power factor is just R divided by the magnitude of Z, and the magnitude of Z is found with these equations here, depending on whether you're in a parallel or series or whatever. Um, so yeah, basically the thing that was really confusing me was like how I was able to go from like this cosine and sine stuff back and forth. It's really just because we're changing the total and then we're taking the real part of that change. So now, if we go back to figure out like the power dissipated or whatever, consider that even if you tried using this equation, you'd still have to calculate VR, which is actually IR. So you still have to use the squared current. Um, and so I was getting confused because I was like, well, aren't I just scaling it by a single cosine over here with the I? But it actually looks like there's a I squared there because the VR contains the I, and so yeah. So yes, these are just some interesting things I figured out about current and the power. It kind of finally makes a little bit of sense to me. So thank you so much for watching, and yeah, if you wanted to download one of these files just for mechanics, for example, you can find one at free